my YouTube channel, and this is going to be the video number 34, and we are going to be doing an Mppt solar charge controller using the constant voltage method or fixed voltage method. Right, to start with, safety is number one. I expect that people who try my projects have got electronic working experience or experience with electricity, because electricity has some hazards. Since we are actually going to be doing a power electronics project like the solar charge controller, it has got hazards like fire. It can also have hazard on electrocution or injury. The tools that we use also a safety area to consider. So I expect that people know about electricity and its hazards, and also because this is not electronics training to people who have no prior knowledge of electronics or electricity. I expect that people who try this project have got a tutor or someone who already has some experience with electronics or electricity. Keep our working area free of equipment that we are not using, and also safe for children, that's away from children. And I also expect that a minimum of 10 years is recommended for someone to actually try these projects. I describe the projects as I have done them, and only the description of how these projects work. And the philosophy of my project is that I use recycled components, although there will be new components coming, but mostly I try to use recycled components from old PC boards, enclosures from old computers, and all equipment that is not going to be used anymore. I take those ones and use what I find there. If there is a specific component that I need that I do not have, obviously I buy. Well, there is always many ways of doing some of the projects that I do, and different ways. So my projects are subject to correction, or you can adapt or modify or improve them. And well, I expect also that when you do that, you share with other people. But you can also use it for training. You can use it as a learning aid. You can use it for your own benefit at home, or you can actually use it for industrial application. Required components for this particular project, the solar charge controller, using constant voltage or fixed voltage Mppt method. Well, the computer, because we are not going to program, there is no microcontroller or any programming involved, so some of the equipment won't be necessary, like the big programmer or the, well, of course you are going to need the computer, but the serial port, well, maybe not. Power supply, please, I would suggest you have a power supply that gets up to maybe 60 volts. Well, not safe for people who are not experienced, but at least something that can actually be used to power, to represent a solar module that is a 24 volt solar module that gets up to 50 volts. So 60 volt power supply would be handy. You need electronic components, of course, variables to mount components, or to PC boards to get components from there, soldering iron, obviously, solder wire, the meter, of course, electronic tools or electrical tools, software. Well, software that you may need would be maybe the Proteus development suite which I use. You can get the trial versions or any other free software that you can use for simulation if you want, but this one won't have any simulation as I will show you. Right, you need time, patience, passion, and dedication and feedback. Please do so, and you can write me on my email, that@gmail.com. Thank you. I hope you enjoy electronics. So let's start off with the overall circuit. Let me just change the view here to full screen. Right, now this is the schematic of the solar charge controller that I have built. Basically, I'll show you here. The input, the solar module will be here, and then here you have the pulse width modulation IC, the TL494 from Texas or any other manufacturer. And then here you have your MOSFET, then the inductor here, and then the output to the battery is here, and here the other control circuits. Here you have your power supply for the high side MOSFETs. These are high side MOSFETs. And then here you have your fan control circuit. Here is a circuit to actually check for solar power, meaning the sun, if the sun is still there, and then if it is not there, it goes into sleep mode. And then here is the Mppt circuit. Actually, it's a 555 timer, but so it actually just checks the voltage of the solar modules or solar module that is coming to the charge controller. Right here you have your let me zoom it a bit. Right, your 72 cell module. Although on my real charge controller that I'm using a 36 cell setup, meaning a 12 volt module. There are actually two of them, 150 each, that's 300 watts. And then so you have a maximum open circuit voltage of 22 volts here. So my maximum voltage for the MOSFET, I made it to be 100. Well, I used the 100 volt MOSFETs. I also used the Schottky diodes that are 45 volts. So you have your power circuit breaker here, or a switch of some kind, or even a jack. You have power going on the drain of the MOSFETs, and then here you have your TO494 driving these MOSFETs. Here you can actually use a normal MOSFET driver like the IR2113, the IR2110 series, low side, high side driver IC. Here I used an optocoupler and then a MOSFET and transistor driver there. It's working, and because you have the reference different on the MOSFETs, the source of these MOSFETs are not going to zero or to the ground of the wall circuit. You actually have to have an isolation driver circuit here. That's why the optocoupler. And then here you have a simple power supply, DC to DC power supply that I have used using a transformer isolation method. So this is a transistor relaxation oscillator here, 2 transistors, 2 capacitors, and 4 resistors. And then this circuit will actually, when you power it, it just gives you out a square wave output to drive that MOSFET, and then you are actually driving the transformer here. You have your output here, and then you actually adjust it to 15 volts output, and that power supply is actually for these MOSFETs, because these MOSFETs have got a floating source. So that's why the need for the power supply. And the frequency here matters a lot, so be careful not to have high frequency here. I would say 20 to 50 kilohertz is enough for this circuit, right? So what you have here is actually what is called a buck DC to DC converter. This is a buck power supply, and here the inductor must be able to handle the current that will go into the battery. So at 300 watts you have around 16 amps there flowing, so that inductor must be able to handle that much current. You actually also need to have temperature control using forced air draft, that is a fan. So what happens here, you have your comparator LM393 with a thermistor there, 10 kilo ohm room temperature thermistor, 10 kilo ohm here, and then 5 volts from a regulator or from the TL494. The sleep circuit is like when the solar is present. This is actually like a reference point here, 2 diodes here, 2 voltage drops here, that's about 1.2 volts here sitting there on the inverting point. But there is a solar here at a certain voltage. The comparator switches on that transistor and operates the relay so that the circuit starts to run. And then when the solar power goes out, that's maybe at night, the comparator sees that and then switches off that transistor and relay comes out, the circuit goes to sleep. And then remember, please, all I should say most comparators have got an open collector output, so you must actually pull it up, meaning connect a resistor 10 kilo ohm, 1 kilo ohm, whatever, to the power supply line so that you have a normal operation, just like the fan control. There you must also do that. Right, the Mppt circuit, the most important part on this design is actually a 555 timer circuit. So what it does is basically it checks the voltage of the solar supply. The collected data that I'll show you for solar modules, different manufacturers, different types, different sizes. We are now doing maybe the 36 cell or the 12 volt module, which has got the Mppt voltage or VMP voltage at maximum power, normally around an average of 18 volts, and the open circuit voltage, which is the VOC, normally around 22 volts. So when the voltage is still above 18 volts, you actually have your voltage drop here, that actually is having an output here low. The output will be low. When it goes under 18 volts, which is the VMP, the output at pin number 3 goes high, and then 87 goes low. So what happens, the output at pin number 3 is actually driving a transistor which controls the switching of the back circuit, meaning you either stop the switching of these MOSFETs or you allow them to switch on, just like you would actually also control using the feedback circuit. The feedback of the voltage feedback, that is you have it here coming from there, the output at the inductor there, going back through there, through there, sensed by the input pin number 1 on the TL494. Right, so what happens is, if the voltage has gone below 18 volts, remember the pin number 3 goes high. If you start your the 555 timer, how it behaves. There is a video for that on my previous videos. I think on the solar charge controller that I have done using the 555 timer. I made a description, a full description of how the TO55 timer works. So this output goes high, switches on the transistor, and it grounds there so that the optocoupler is switched off, so no driving of the MOSFETs, turns off, meaning that the solar charging stops. The voltage of the solar module actually rises, and it rises past the maximum power voltage, and when it goes there, this voltage gets to a point where it actually the threshold voltage, and then it switches the output pin number 3 to 0. So this turns off, and then the pulse width modulation IC is running, so you start charging again. The 555 timer output number 3 is low. The discharge pin number 7 is actually a low. It's a transistor that is switched on. It brings a low on pin number 7, meaning the LED comes on, shows that it is charging, and then the optocoupler switches on also. And these MOSFETs are actually what we call the back current switch. These two MOSFETs are actually back current switches, meaning that when there is no sun, it must close the current path from the battery going back into the solar modules. So they are actually back current switches. Right, so I made a description on back current switches, I think, on one of my videos on solar charge controllers. So this here also acts as an indication and also by current switch output. So that's how this is working. The Mppt part is you compare the solar output voltage to the maximum power voltage. If you have a 72 cell, which means the VMP is around 36 volts, so you actually adjust this resistance so that you have that voltage here setting the voltage settings, and this is coming from a 5-volt supply of the 555 timer. It's a 1/3 of 5 volts. I've used 5 volts here. Here's the voltage regulator here, 5 volts output. This regulator is powered from the battery. It's a 12-volt battery. If you have a 24-volt battery, I think you can do that, or you can actually have another power supply that will give you 5 volts output to power the 555 timer. So the 1.67 volts is actually 1/3 of 5 volts, and 3.33 is actually 2/3 of 5 volts. That's where it is coming from. So whether you have 72 cell here or whatever voltage that you put in there, you can adjust these resistors so that they give you these voltages at the voltage that you would actually have chosen. That is the maximum power point voltage. Normally it's 18 volts for 36 cell module, and 37 or around 36 volts for solar module. Please remember to actually adjust this voltage. Allow some hysteresis, like you would actually go to 17.5 volts for VNP. the Mppt charge controller. As I have made it, we're using a back power supply. To start with, here is the power switch modulated IC, the TO494, and here are the MOSFETs. You can see the two MOSFETs here, and then here the Schottky diodes.